Hello all, today we will discuss about buck DC-DC converter with digital voltage mode control. In digital implementation, the output voltage is sensed by voltage divider and then applied to an ADC input pin. As soon as the sampled output voltage is converted into digital domain, then we can calculate the digital error by the difference between a digital reference and the sampled data. Then this digital error is applied to the digital compensator, and the output of the digital compensator is going through a anti-wind-up mechanism, and then it goes to the PWM block to generate the needed duty cycle. The basic principle inside the PWM block for the duty cycle generation is similar to the analogic implementation. So we have a digital comparator this time, a digital ramp, which is realized with a counter, and which is actually one of the input of the comparators, and the other input of the comparator is actually the output of the digital compensator. Well, we know the MCU normally runs on a clock frequency. We can define the tick as the period of that clock. Normally our application has let's say 100 kilohertz switching frequency. For instance, here it is an example. If we have a clock frequency of 80 megahertz, we can calculate the number of ticks we have in a switching period by simply doing the ratio between the clock frequency and the application switching frequency. So in this example, 80 megahertz over 100 kilohertz, we end up with 800. So that means that the comparator has to, the counter has to count from 0 to 799. Eventually, this 799 will be the value that has to be introduced in a specific register within the PWM module. The gain of this comparator is simply the duty cycle over the ramp or over the number of ticks if you want. So in the end, it's simply 1 over 800 for our example. We have this GK block that has to negate the gain of the resistor divider, the gain of the ADC converter, and the gain of the digital comparator. So this is why GK has this expression here. The gain of the ADC is simply the output over the input. So output would be the 2 to the power of number of bits minus 1, and input is the full ADC, analog ADC input range, which is actually the ADC ref. So this is the expression, the gain of the ADC. Okay, now if for our previous examples, when we did an analog buck converter, we had for the compensator a transfer function in analog domain, meaning in Laplace. So we had the HC of S. In digital world, we would need the linear difference equation that will be implemented in the software, and this linear difference equation will generate a new reference that will be compared in the digital comparator by the digital ramp to generate the needed duty cycle. So first, what we need to do is to transform the analog transfer function HC of S in a discrete form like HZ, by using the Z transform. And then we will manipulate this the form of the Z transform to get the linear difference equation. So in order to do this, we use the most common used method is the bilinear transform, also called known as Tustin, in which actually the Laplace operator will be replaced with this expression where Ts is the sampling period. This is an approximation. In principle, the lower the crossover frequency in respect to the sampling frequency, the better will be the approximation. We have a small example to work out. We have a low-pass filter, RC, with its transfer function in analog domain is 1 over 1 plus S times R times C. What we need to do to go into discrete or Z transform is to replace the S operator as with Tustin approximation. We do this, and then by mathematical manipulation, we need to isolate y of z, and we will end up with an expression in this form. And from this expression, actually, we can then replace the z by n, and for instance, x of z times z at the power of -1, we will replace with x by n minus 1. So xn is actually the value of the current sample. Xn minus 1 is the previous sample, the value of the previous sample. Y of n is the output of the compensator calculated within the current sampling interval, and y of n minus 1 is the previous output, previous calculated output. So in general, from a discrete transfer function h of z, we will have of this form, the on the n of z, or numerator, let's say, we'll have the b coefficients, and on the denominator we'll have the a coefficients. And from this form we can easily write the linear difference equation by having this expression. So now actually what we will do for our digital compensator, we will start with an analog design. We know the transfer function in analog domain. We will translate it into discrete domain, and then we will have the this will be the form of the linear difference equation. The parameters, the b's and the a's, I was not extracting by myself. I was just looking on a paper which is from Dr. Ali Shirsavar on a series called Digital Power Supply Loop Design Step by Step. Part 2 is published on EE Power. You can see all the details there. You can also visit biricha.com for more details about the digital power supplies. Okay, something about the phase erosion mechanism. So basically, every time delay we have in the digitized, let's say, sampling of the output voltage and digital processing will introduce a phase loss. Here it is an example. We have the red trace is the an analog signal. We are sampling it at fixed sampling period. And then we have a sample and hold waveform, which is the blue one. So at every sampling pulse, we are sampling the output voltage, and then we'll stay at that value until the new sampling is happening, and so on. And if it will be to reconstruct the analog signal based on this sample and hold signal, we see that it will be delayed in time exactly by half of the switching period. Yeah. So in general, we have a phase loss, also called phase erosion, given by this expression is 360 degrees times the frequency at which we want to see how much phase loss we have times the time delay. Okay, so the sampling and reconstruction process in the digital implementation of the power supplies will generate this phase loss. So we have it here. For us, it's important at cutoff frequency, because we want a certain phase margin to have, and because of this phenomenon of phase erosion, we'll normally end up with less than what we expected to have. So we have a phase loss due to the sampling and reconstruction. And we have another time delay, which is from the moment within the switching period when the ADC is triggered to sample until the moment when the new output of the digital compensator is used. So this is normally happening in the next switching period. Okay, so that means that the if we sampling the output voltage at the beginning of the of one of the switching periods, then the calculated the new um, um, calculated output of the new output of the controller will be used in the next switching period. So that means the maximum delay is one switching period, yeah, if we do this. So actually the phase loss due to the calculation is given by this expression here, where this Ks is actually the number of sampling period. Of course, we can sample at, I don't know, a different value for the. I mean, we we intend to have a sampling of the output voltage in every switching period, but it could also happen at 2 or 3 or 4 or 5 switching periods. That this is also possible. But the higher the time delay, the bigger the phase loss. Okay, so in our analog example, we used the switching frequency of 100 kilohertz. We want to use the same for the digital implementation, and we targeted cutoff frequency of 10 kilohertz. Yeah, as I said, we will sample at every switching period, so the sampling period will be 10 microseconds. So now let's calculate what will be the phase loss due to sample reconstruction and due to the calculation. So we end up with 18 and respectively 36 degrees. That's a total phase loss of 54 degrees, which is very big. So to reduce this phase loss, we will select the lower cutoff frequency. So we'll go to 5 kilohertz, so half of initial value of 10. That means we will expect a phase loss of only 27 degrees. So this phase erosion phenomenon is one of the reasons why the for digital designs we need to select a cutoff frequency which is kind of smaller or equal with the switching frequency over 20. This is a good practice recommendation. It doesn't mean that you cannot have a cutoff frequency or select a cutoff frequency which is higher than this number. Okay, so now since we have a different cutoff frequency, we need to update our power stage to satisfy two conditions. So we have the voltage deviation as step load and the cutoff frequency, which must be 2 to 3 times the resonant frequency of the power stage, because at the resonant frequency of the power stage we have a pole pair that introduce a sudden change in the phase, and we don't want to be close to this. So since we want to have a synchronous rectifier buck converter, we can operate from 0 amps, I mean no load, to 2 amps. We know that we will have a DITT of 1 amp per microsecond as we used in the previous examples. And we know that the maximum voltage deviation on a step load is 250 millivolts. So we will have variation in the load current from 0 to 2 amps, so it's 2 amps. So with those data, we can calculate what would be the requested output capacitance, and this is like 255 microfarads. Now this value is pretty high. We can't use anymore yes, we can't use the previous ceramic capacitor we considered in the analog design, but we will need like 15 pieces in parallel, and this is a bit too much. So we will focus on the electrolytic capacitors. We know that for electrolytic capacitors there is a problem with the higher value for the ESR, but nowadays we have hybrid polymer caps with very low ESR, so there are options to choose from. Yeah. Then we say, okay, out of the 250 millivolts, maximum voltage deviation, 1/4 should be generated by the ESR, and the rest of 3/4 by the capacitance. That means we can recalculate the output capacitance, and we end up with this 340 microfarads. And we can calculate what would be the maximum ESR we can accommodate, and this would be 31 milliohms. Well, looking for a suitable capacitor, I found on Würth Electronic webpage by using their Red Expert application, 220 microfarad hybrid polymer capacitor. We can see it has an ESR of only 11 milliohms at 100 kilohertz, 15.5 milliohms for 5 kilohertz. It's true that for 1 amp per microsecond, probably we will be here in this megahertz range, which is in the same 10 milliohms range. It has a tolerance of plus minus 20%. That means the minimum capacitance I will consider is 176 microfarads. That means for the 340 I will use 2 in parallel, so I will end up with this 352 microfarads. Well, normally having such a small value for the ESR, we can also go with lower to lower the capacitance, but for the moment we will stay with 2 parallel capacitors, and I will consider this 352 microfarad capacitance in our example. Okay, now what we have to do is to calculate the resonant frequency of the power stage to check if condition 2 is satisfied. So we have the value from the analog design for the buck inductor and the new value for the capacitance. Calculating the resonant frequency, we end up with 1.4 kilohertz, which is about 3.6 times smaller than the selected cutoff frequency. So that means condition 2 is satisfied. Now we can go to calculate the digital controller. As I mentioned, we will do the design first in the analog domain, and we will keep in mind that we need to add additional 27 degrees for the desired phase margin, and then we will convert to the linear difference equation. So the targets in digital design, we have a cutoff frequency 5 kilohertz and the phase margin 50 degrees. For the analog, we'll have cutoff frequency 5 kilohertz and a phase margin of 77 degrees. Now, in order to use the K-factor method, as we did it for the previous examples, we need to know or to have a Bode plot for the plant transfer function to extract the gain and phase information at 5 kilohertz. So for this, I updated this small simulation with a new output capacitance and run it. We will placing a cursor at 5 kilohertz. I end up with, or I extract these values. For the gain is minus 0.365 dBs and phase is minus 173 degrees, and we know that the sampling period is 10 microseconds. Okay, to easily calculate or for iterative calculation or for yeah, I create a small Python script. We have as the input switching frequency, we have the cutoff and phase margin, the values extracted for the plant transfer function, and then it calculates the parameters needed for the linear difference equation. Yeah, so it outputs the frequencies where the poles and zeros are placed and the parameters. This is what I am mostly interested in. So I will simply copy and paste this to our C++ file. Okay, so now we set up a new simulation, or I set up a new simulation. We have here a DLL block X1. So we are sampling the output voltage by these resistor dividers R2 and R3. You see both are 10K, so the gain is 0.5. It goes to the ADC2. ADC1 samples the input voltage, but is not going to be used here in this example. It will be for a later development to implement a feed-forward gain. We have the two PWM outputs, PWM H and PWM low. We have, of course, the reference for the ADC and 2 test pins, which are mainly used in during software development. On a closer look for this DLL block, I defined some input parameters like switching frequency, maximum duty cycle, dead time in between PWM high and PWM low, desired output voltage, gain of the resistor dividers, soft start time, sampling period, number of ADC, number of bits for the ADC, ADC delay. This has to do with the trigger. When the ADC is triggered, the conversion time of the ADC, then the delay when until or yeah when the linear difference equation inside the software is executed within every switching period, and this is the execution time of the linear difference equation. Okay, so the code will be basically, so we will have a ramp here, and based on the ramp, we will have a PWM signal, which has also a limit on the maximum duty cycle. Then we have an ADC trig generator. It's like a clock for the ADC, and then it's this run 3P3Z. It's like a clock, if you want, for the digital regulator. Yeah, so we can play with this ADC del. We move the moment when we are sampling the output voltage, and then here we can also play when the moment when we initiate the calculation of the digital regulator and how much it takes to calculate the linear difference equation. In principle, we need to have the new value available prior to or before starting a new switching period. In the code, I will update this on the rising edge of the PWM signal. Okay, so depending on the selections or the choices that are selected in the when the C++ file is generated by the template, this memory allocation is by default included. I include the CMAT to for the functions I will use for the ramps. And then we have definition of the pins. I simply copy and paste the parameters from the Python script here. Then here we have the structure defined, and here are the defined type of data for the input and outputs and input parameters. Then here we will start actually our code. We have the ADC trig generator, the run 3P3Z generator, ADC sample and conversion, soft start ramp, reference in digital, and new error calculation. At this point, the digital compensator function is, and we have here the linear difference equation, clamping y of n. Okay, then this is the GK, the compensation gain, the comparator, and the output stage. Yeah, and here we are simply generating the PWM high and PWM low. And we have 2 test pins, and for this test 2, we have actually the other input in the digital comparator. Yeah, it's the output of the digital controller times the compensating gain. Okay, then running the simulation with the Bode statement, we end up with a cutoff frequency in open loop of 4.93 kilohertz and a phase margin of 51.3. We then, I wanted to double check what the power stage looks like and what values I have at 5 kilohertz. I simply do this by changing the options in the .Bode statement, and I end up with 0.318 dBs and minus 171 degrees, which is slightly different values. Therefore, I introduce the new values in my Python script and rerun it again, take the new parameters, paste them in the C++ file, compile it again, and run the simulation. And finally, I end up with 4.96 kilohertz and 49.1 degrees. We can, of course, also have a look how the compensator transfer function looks like by using this test2, which is TP2. So in this body out, I use TP2 instead of out. What we can notice here is the because we are sampling once at 10 microseconds, we have basically a system 100 kilohertz system. So at 50 kilohertz, it is visible the first Nyquist frequency that manifests as a gain dip here. So this gain dip is another reason why in digital power supplies the selected cutoff frequency must be lower than switching frequency over 20. Okay, so up to now, we considered a worst case scenario in which we sample at the beginning of every switching period, so Ks equals 1, and this gives us a phase loss due to the calculation of 18 degrees. Now, let's assume that we will delay inside the switching period by 4 microseconds the time when we trigger the ADC. That means the Ks will be 0.6, and the new calculated phase loss due to the calculation will be only 10.8 degrees. That means we will have a boost in phase margin of about 7.2 degrees. So the expected phase margin will be like 56.3. So I updated this ADC del to 4 microsecond, and I run the simulation again. What I ended up with was a cutoff frequency with 4.99 kilohertz and a phase margin of 56.5. So there is a small 0.2 degree difference. I cannot explain it right now, but in general, the theory is it is working, is confirmed. Okay, now I wanted for the dynamic behavior. So the load resistance in the transient simulation was replaced by a pulsed current source, that will act as a current load and will generate the change in load current from 0 amps to 2 amps in back in 2 microseconds. So you can see the red is the current of the current source that acts as a load. In green, we have the current through the inductor, and here the output voltage. And you see we have only 170 millivolts overshoot, and 100. I don't know how much. 80 millivolts undershoot. So we are well within the maximum 250 millivolts allowable voltage deviation, and that's because actually the ESR is much lower, so its contribution is smaller. Okay, so that is for today. Thank you for watching and for your attention. Bye.